is, where's the killer app? So right now the killer app for IPv6 is, do you need to be connected to the internet? Which, ha ha ha, but if you're looking at a lot of stuff or a lot of services, that's really where it's at, especially in the mobile space. So right now, we're gonna hit critical mass, which is 10%. We're gonna hit that in 2014. So sometime in the second half of 2014. So that's why you have these two forces. Again, I mentioned you have depletion and you have adoption, right? And I kind of thought, because originally it was gonna run out this year, but I think we're kind of past that. I think depletion is almost not gonna matter. When we get to 2014, you're gonna see, it's gonna be so obvious that it's ramping up, especially on the mobile side, because there's no legacy. It's just gonna work. There's gonna be a huge, the floodgates will open. And once we hit the second half of 2014 and we get to 10%, that's when you get the killer app. And this is a good thing to watch now, because I don't, for anybody in this room, I don't think learning IPv6 is a monumental task. It's just time. But look at it like this. So most of you have been in the position of hiring somebody to support your company or to help you out. So if somebody came in and said, hey, I am a DECnet and an IPX expert. I know it backwards and forwards. I've never done anything with IP, but networking is networking. And so let's say you have a 1,000-node network. Are you gonna hire me to run your network with no IP experience, just with DECnet and IPX? I mean, come on, networking's network, right? No takers? So with IPv6, I mean, there are a lot of similarities, but in Radia Perlman's interconnections book, she actually said that IPv6 is closer to DECnet than IPv4. I mean, I don't think it's that hard to learn, but it is definitely not the same. And there are a lot of differences. There's a lot of functionality that is significantly different. And so here's the thing. You don't want to wait until the end of 2014, when you have to know it, and then say, oh, maybe I should learn something about this. I would give yourself, what I tell most network engineers, I would give yourself at least 3 to 6 months to ramp up. I'm not saying to be an expert, but at least to be proficient. Now, could you learn it faster? Sure. I mean, it just comes down to how much time do you want to devote. I'm thinking like, maybe a couple hours a week or something like that. If you're willing to be 100%, you can learn it a lot faster. But I'll tell you right now, you're not going to learn in an hour presentation, and you're not going to learn in a week. It's going to take you some time. So that's why I'm trying to show this now, go around and talk to people, because I'm a consultant, but I'll tell you, I don't want to get into 2014 and have 100 calls a day like, oh my God, can you help us deploy? I don't want to do that. I don't want to do that, right? I have plenty of work right now. So I want to get the word out. Please don't wait until the end of 2014 to look at IPv6. Okay, so most of this I've already talked about. I don't want to belabor it too much. Other than the one thing I do want to hit, just because, well, there's two things I want to hit on this. So one is, I know this from talking to a lot of my customers. A lot of people listen to Gartner. I mean, you can argue about, are they off or not? But, just the fact that everybody argues about them, they definitely have some influence in the industry. So if you listen to Gartner, by 2014 or 2015 at the latest, you should be on the IPv6 internet. And their statistics are even further along. They're saying by 2015, 17% of the internet will use IPv6, and 28% of all new users. So 28%. That's pretty significant, right? Ask your marketing department if they want to ignore that. And again, the biggest thing though is at the bottom. And this is again from Gartner. The average sizable enterprise will take 3 to 5 years. And I mean, that sounds like 3 to 5 years. I mean, how could it take that long? And again, imagine that your entire network is running DECnet. And you have to switch everything. Everything that has an Ethernet jack, everything on the wireless, all your applications, everything has to be updated. I mean, how long do you think that's going to take you? You think you're going to do it in what? 2 weeks, right? 2 weeks, a couple late nights. So this is a pretty big project. So knowing that, and if anything, Gartner's estimate is conservative, knowing that a huge portion of the world is going to be using IPv6 as their preferred way to get, knowing that mobile devices are the predominant web access device this year, and that's where everything is going, right? I mean, I don't, will it take you 3 to 5 years to get ready? No, it won't take you 3 to 5 years. But it might take you at least 3 to 6 months. Right? So knowing that this is coming, now is the time. You don't have to necessarily go out and take action today, but you at least need to see, where am I at? Right? You should be able to answer the question, like for me and for my company, where am I at? Right? You should have a purchasing policy in place so that anything you buy supports this, or if it doesn't, you're at least negotiating a discount. And you should be looking at, okay, let's say that beginning of 2014, I want to have this running. How much time do I need to give myself? Is it 3 months? Is it 6 months? Right, so this is where you should be at. You should at least have a plan for where you're at and how long it's going to take. All right. Probably talk too much about the first couple slides. So, like I said, I'll provide these. I can tell you we're not going to get into everything. I'm going to go through this fairly fast. So I will say right now, if you have never seen IPv6, well, if you've never seen IPv6, and I go through this, and you get it all in this quick presentation, I'm really impressed. I want to get your business card. So my expectation is you're not gonna. This is not gonna make sense if this is the first time you've seen it. But at least you have an idea. You'll have these as reference, so you can always go and flip through later. But like I said, it's going to take some time. So don't get frustrated if everything doesn't make sense right away. Okay, so the big thing with IPv6 is the address space is 4 times as big. What does that mean? Like we talked about initially, the addressing is essentially unimaginably large. I mean, and people will do all these crazy analogies about like everybody could have a billion internets personally and whatever. I mean, the bottom line is the address space in IPv6 is so vast you can't even imagine it. So the point of this is this should last at least 50 years. We'll have plenty of addressing. So, which is how an addressing system should be, right? You shouldn't care. When I provision a wireless subnet, there should be enough. It's just like a street. There should be enough addresses that it doesn't matter how many devices I put on that network, it'll just work and I'll never have to touch it again. And that's what IPv6 provides. Okay, I'm not gonna go through everything just in the interest of time. So two big things. Fragmentation is totally different in IPv6. This is one of the major changes. In IPv4, anything can fragment a packet. In IPv6, only the sender can. So intermediate devices like routers and switches no longer fragment devices. So if your packet's too big, they will basically just send an ICMP message back that says, your packet's too big and I'm not sending it, see ya. So this is an important point because a lot of people in the IPv4 world block all ICMP traffic. If you do that in IPv6, your IPv6 network will not function. So that's important to remember. The other big thing is with fragmentation and with all these options, none of these are in the header anymore. The IPv6 header is very simple. So all these options become extension headers. So extension headers, they sound kind of cool at first, but this is where a lot of the complexity is in IPv6. So any kind of option I want to do, like with multicast options, with resource reservation, with IPsec, with mobility, with fragmentation, anything like that, those all become extension headers. So I basically have the base packet, and that has the next header field. The next header is loosely like the protocol field in IPv4, so my next header can be, one of a bunch of different things. So here are some of the popular ones. There's a whole bunch of them. And then I can have this big header chain. So right now, it's easily possible to have up to 8 extension headers. So this can create some complication in terms of your access lists and firewalls. This is still very much a work in progress in terms of how to secure all this. So just be aware that I have all these for now. Okay, I talked about fragmentation. There's no more ARP. ARP is gone. So one thing I recommend, if we get to it later in the presentation, is make yourself an IPv6 only network. Because it's kind of like if you want to learn to speak Spanish. If you take a bunch of Spanish classes here and you stay around English speakers, how good do you think your Spanish is going to get? Probably not so good. But if you take a bunch of Spanish classes and you go to rural Spain, then how good is your Spanish going to get? It's going to get a lot better. right? So the same with IPv6. You won't realize how much of a crutch all of your IPv4 knowledge is until you put yourself on an IPv6 network. And you'll discover a lot of subtle things are different. All right, so I'm not going to go through all these. You know, consider this reference material. Just suffice it to say there are some significant differences. Okay, so this I try to do. I do a lot of internal training, so you know, to try and ramp our staff up to. So I try to think about what are the major changes, because I get this question a lot too. What's really different in terms of V4 versus V6? So we talked about size. Multicast is another big one. IPv4 does not have scalable multicast. It just doesn't. IPv6 has scalable global multicast built in. What this means is with IPv6's native capabilities, we could have things like radio and TV and cable and stuff like that could be globally distributed through multicast. It's just built into the protocol. You know, they had the hindsight of looking at what didn't work with IPv4 and fixing it. So that's actually, this isn't going to be something out of the gate, but that's a pretty big one right there. Scoping. So how many of you have ever plugged your, either used a wireless network or plugged your computer into an Ethernet and you get one of those 169.254 addresses? Those are what's called link local addresses, which I never really understood until IPv6. So IPv6, all interfaces have a link local address that starts with FE80. And what link local really is it means that address is only significant on that link. It's not routable. And there's a whole bunch of things we can do, like for example, with DHCP and IPv4, I have to kind of fake having an address to get an address. I have to do a bunch of hacks with the raw socket. And IPv6, I always have a link local address. So if I need to get a globally routable address, I use my link local address and multicast out a request saying, hey, I need an address. And then somebody will listen and say, here you go. So there's a lot of interesting things you can do with that. So scopes are different. Multiple addresses per interface. So in IPv4, you can have multiple IP addresses per interface, but it's more the exception than the norm. Right? If you look at a typical client, you're only going to have one IP per interface. Not in IPv6. In IPv6, you will pretty much always have at least 2, and you can have 10 or more. So everything, routers, switches, end systems, mobile devices, they will all have multiple addresses. So this kind of creates an interesting challenge. If I'm writing access controller firewalls, that's a real interesting challenge, right? Because in the IPv4 world, I kind of assume that everything has an address. But that assumption no longer holds with IPv6.
Switches, with that not layer 3 switches, the switches have an address?
Yeah, because even if you look, well, if it's a dumb switch, it won't. But most switches have management. So your management interface is going to have multiple addresses. Okay, so some of this is history. I'm kind of a history buff, so I went back and read a lot of this. Plug and play. So anybody who remembers the IPX or even the DECnet days, the cool thing about IPX is you plugged in your computer and it just worked. So they tried to model that in IPv6. So there's a lot of auto-configure operations. So if I have a router in IPv6 and I plug anything into the same segment or network as that router, it's just going to automatically configure an address and start working. So some people really like that. People in companies usually don't like that. Mm-hmm. So keep in mind that's another big difference. In terms of, there's a lot of cool security ideas. I don't think there's anything I've seen yet that I'm convinced is going to take off, but I think there will be things. So I'd say there's a lot of possibilities. So, you know, with these two things, you know, there's not, I mean, the big thing is just the size. That's really why you want IPv6, is it's just the massive size of addressing. But there are some significant changes, right? Because some people will be like, there's no difference, it's the same. That's not true. There actually are quite a few differences. Okay, and this is, I'm not going to spend time on this, but just to kind of give you a taste, here's some examples. You know, here's what it looks like, because I think this is good for comparison. Here's what it looks like in the IPv4 world. Here's what it looks like in the IPv6 world. And then just to give you an idea, right? So IPv6 is essentially the IPv4 internet times 2 to the 96. That's the size. So I mean, the way I describe it is it's just unfathomably big. I think it's like some undecillion number, but I mean, it's meaningless, right? It's essentially enough to last a long time. All right, so Jim, I know originally I was only supposed to go to like 7:46, so should I go a little longer?
Go to about 8 o'clock.
Go.
All right, so I apologize for not managing my time as well as I should have. Okay, so IPv6 address structure. This is good reference material. I've actually heard somebody say these are called hextets. I don't know if that's official or if somebody just made it up. But essentially you have 8 groups of 4 digits is what makes up an IPv6 address. They're separated by colons. They're not case sensitive, but you prefer lowercase. And there's abbreviations, right? So I'm just gonna kind of gloss through this. But I do have some examples. So I have my IPv4 and IPv6, and that 2001 DB8 is for documentation. So you'll only see this in documentation, you won't see it in the wild. But just as some examples, so this one in the middle, that's a full IPv6 address. So can you see how DNS will become more important? How many people think you can remember that? So they're a little bigger. But you can compress them, and this is just an example, right? So the leading 0 can always be omitted. Kind of like in decimal. If we look at decimal, I can say 010. 010 is the same as 10. But I can't say 1 or 01, right? I can't lose digits to the right, only to the left. So if you think about this in the decimal system, it's the same way, right? And I struck these through. These are examples of doing it wrong. So leading zeros, just like in decimal, just like you're used to right now, can always be omitted. Also, if I have a long string of zeros, I can compress that long string with a double colon. Now, if you look at older text, it'll say you can do it anywhere. That's since been amended. There was a newer RFC with a canonical form, and basically in the newer RFC, you have to actually compress the longest string of zeros, as opposed to being able to do anywhere you want it. And the point is, think of it from a program point of view, right? So a lot of people I heard do Perl, Python, things like that. You know, to keep your sanity, they wanted to have more consistent rules. So when you're parsing these addresses in logs or something like that, you don't have to do all these crazy things. So that's why we came out with clear standards.
The last line there, you compressed out the 2 double zeros with a double colon, with 1 double colon.
Exactly.
So it didn't take 3 colons to do that?
Pardon me?
It didn't take 3 colons to do that?
No, just 2. So the double colon represents a string of zeros. In fact, if you look at the previous slide, like the one at the bottom, they can actually get pretty small. Like that's a multicast address, and it's actually pretty small.
So the last one can never be 0 then, right?
Well, the unspecified address, which is all zeros in IPv4, is just colon colon. And the loopback address is colon colon 1. That's as small as it can get.
But the assumption is that you're only going to have one of these in there then, right?
Yeah, you can only have one, otherwise it couldn't be.
Right, okay,
yeah.
that's
Yep.
It needs to end up being 8.
Yeah, and you have to be able to expand it into this one in the middle.
I think of octets, but you said
Hextets. It's 8 groups of 4 hex digits. So hextets is what I've heard.
Cool.
I don't know if that's official, but sounds good. Okay, so scope. So just in a nutshell, like I said, link local are only significant on the network. I also have something called unique local. So in the IPv4 world, we have the private or the RFC 1918 addresses. So the problem with the private addresses is they're not unique, like we talked about before. And the real problem with the RFC 1918 private IPv4 addresses is we have overlaps. So anybody who works as a network engineer, you do these B2B connections. And then you find out that the company you're doing the B2B connection with, you have overlapping private addresses, which means you have to do double NAT, right? How many people like doing double NAT? Or like trying to support it, yeah. So we try to learn from that lesson in IPv6, and with EULAs, you actually use a randomizer to generate the address. So the idea is if everybody actually listens to the directions, well, I guess we'll see, but if they do, and they use the randomizer to create the prefix, those addresses should be unique, thus we avoid the disaster we have with the RFC 1918 addresses. So that's where that unique local comes from. The global, this confused me for a while, so all current global addresses start with 2000 colon whack whack 3. And it's not to say that there can't be other ones, but this is the only prefixes that's been allocated by IANA. So in the future, you know, there's going to be more, but for now, this is the only one that IANA has actually allocated to the 5 regional internet registries. We also have lifetimes. I'll just mention in passing, lifetimes are interesting because they let me change between addresses, right? So on IPv4, renumbering is really a huge pain. And IPv6, because we can have multiple addresses, we can actually transition from one addressing scheme to another. We can actually phase it in.
Because it can assign both?
Yeah.
Same, yeah.
Yeah, because you can have 10 addresses. So you can transition from one to another.
You say address lifetimes that you talk